All right, yeah, so I guess it's back here. Where do you want me to be for presenting?
This is fine.
Okay.
There's no
All
problem.
right. So it's my pleasure to present, to introduce Kayla. She started working with me actually last fall, and those who were here yesterday saw Kavita, and they were working on a project and with another student who was working with this as well. She's graduated, no longer here. And they actually spent this last fall compiling this data all into what we're hoping to be a published paper. So we're sort of presenting this sort of combined feature within this area of all we've been working on almost for a year now. So Kayla, I'll let you kind of explain what we were doing.
All right, so this was some collaborative research that we decided to evaluate. We wanted to determine the utility or usefulness in using Xenopus frog embryos to determine teratogenic versus non-teratogenic potential of chemicals. So we decided to evaluate two substances, the first being butane hydrochloride, which is widely used as a local anesthetic. It's a known teratogen and has been shown to be cardiotoxic. The second being sea salt, a known non-teratogen, comprised mainly of sodium chloride and other salts. It enters the environment mainly through the evaporation of salt water and also through road de-icing salts. So what is a teratogen? A teratogen is essentially any substance that can cause malformation or birth defects in developing embryos. The LC50 value down there is basically the measure of how much of a teratogenic substance will kill 50% of a tested population. Similarly, the EC50 value is the measure of a teratogenic substance that will cause malformation for 50% of a tested population. Then the TI, or teratogenic index, is the comparison of the LC and EC50 values. So our experimental procedure was the FETAX assay, which is a 96-hour test that uses the Xenopus laevis embryos in order to investigate the potential of substances to cause malformation, mortality, and growth reduction. The Xenopus embryos are ideal for use in the FETAX assay because they develop rapidly and are easily treated with chemicals. So our hypothesis for these experiments were that butane hydrochloride would have a higher teratogenic index than sea salt, as well as cause more consistent malformations and a greater reduction in embryo length. So we followed the ASTM's standard guide for conducting the frog embryo teratogenesis assay Xenopus. We used L-cysteine and human chorionic gonadotropin, plastic petri dishes, and disposable pipettes. And the Systat13 was the statistical analysis software used for our data graphs. And ImageJ was used to measure tadpole lengths at the end of each experiment. So to begin our experiments, we had a male and female frog that was injected with 200 units of the human chorionic gonadotropin to induce breeding. Those frogs were maintained in the lab for a 12-hour light and dark period and fed daily. They were maintained in a false bottom breeding chamber so that once eggs were released, they could gently and easily be retrieved by removing the false bottom. So as you'll notice in the image that I included, once eggs are released, they're encased in a jelly-like matrix. And before we could begin our experiment, we had to remove that casing. We separated a portion of the matrix into a petri dish and added the L-cysteine to it and swirled the contents for about 1 to 3 minutes so that the embryos could be dejellied. Then the embryos were gently rinsed with FETAX solution to remove all traces of the L-cysteine. And then we sorted through all the embryos to remove any damaged or unfertilized eggs. So aside from our 4 controls that we had, for each experiment, we had 4 concentrations, each one with 2 replicates, so a total of 8 petri dishes. And each petri dish had 20 embryos, giving us a total of 240 total embryos for each experiment. The embryos were maintained at 24 degrees Celsius in the dark. Every day we came in and made new solutions and changed out the old solutions, as well as reported daily mortality. And at the end of the 96 hours, when the embryos were fully developed tadpoles, we were able to report mortality, malformation, and embryo length. aside from Systat 13, we used Probit, which takes the concentration and plots on a probability scale and calculates the LC and EC50 values. ANOVA compares the overall values of the controls to the experiment. And the Bonferroni test is used to prevent insignificant data from appearing significant. So our results for our controls for bupivacaine for all 3 experiments was a 2.5% mortality and 7.7% malformation. And then for sea salt, 8.3% mortality and 4.4% malformations. So for our experiments for bupivacaine, on the far left there for our experiments with the red being mortality, we noticed that for concentrations that reached about 50 milligrams per liter and above, resulted in a greater increase in mortality until it reached about 70-75 milligrams per liter, which ended up representing our EC50 value for the potential that it could kill 50% of the population. And similarly with our growth graphs, the increase in the concentration, the greater reduction in length. And these are some of the malformations for bupivacaine. They mainly occurred in the gut, with a couple being spinal and edema. For sea salt, we noticed that for concentrations 4 and above, resulted in a greater mortality risk, with our EC50 being about, our LC50 being about 4.69 and above. As well as with our growth graphs, the higher the concentration, the greater reduction in length. And those are our sea salt malformations. Also, most of the malformations did occur in the gut, with a few being spinal and edema. So overall for our 3 experiments for bupivacaine, concentrations of 75 milligrams per liter and above resulted in 50% tadpole mortality. The higher the concentration, the increase in malformations and length reduction. And similarly for sea salt, concentrations of 4.69 grams per liter and above resulted in 50% tadpole mortality, with the same being the higher the concentration, the increase in malformations and length reduction. So overall for our summary table, the TI, or teratogenic index, is essentially the comparison between the LC50 mortality and the EC50 malformation values in order to rate the overall impact of a teratogenic substance on 50% of the population. The NOEL is our no observable effects level, and the LOEL is our lowest observable effects level for our experiments. And the MCIG is just the minimum concentration to inhibit growth, which was at least 50 milligrams per liter for bupivacaine and 6 grams per liter for sea salt. So overall for our experiments for bupivacaine, most of our malformations occurred at 75 milligrams and above, and they mainly consisted of gut with a couple exceptions. For sea salt, we had fewer malformations since most of the tadpoles did die at concentrations 4 and above. Most of the malformations were also the gut malformations, with a couple spinal, severe, and edema. So overall, our results were supported by our hypothesis in that the higher concentration of sea salt and bupivacaine, the higher mortality and malformation rate, as well as the impacted tadpole lengths. We definitely concluded that bupivacaine is highly teratogenic and sea salt is of little to no teratogenic potential. And lastly, a big thank you to Meredith, Brittany, and Ash for their participation and support throughout the work, as well as the JSC Biology Department for their support. Thank you very much.
Any questions for our speaker? All right, let's thank our speaker again.